On the mathematical structure, we consider on the set of complex numbers described here, the set of all the numbers z, where the real part x and the imaginary part are real numbers. There exists a strong connection between the set of all the space of all the complex numbers and the real space, two-dimensional real space R2. Here is described the algebraic structure. Here we have a structure of vector space of dimension 2, the addition of the vectors, the multiplication of a vector from R2 with the real scalar lambda. In a very similar way, on the space of complex numbers, we have the addition. The addition is the real part. Here is the sum of the real parts. Here the addition is by components. The first component is the sum of the first components of two vectors. The multiplication with the real scalar lambda. We have to multiply the real part as well as the imaginary part. In this case, lambda multiplied by a vector, we have to multiply each component of the vector. You know, this is a real vector space of dimension 2, and in a very similar way, the space of all the complex numbers has a structure of real vector space also of dimension 2. The mapping defined here, the vector with the component x, y goes to x plus y, I, is a linear isomorphism. Evidently, this is a bijective mapping, and also it is linear. For example, the vector with the component 1, 0 corresponds through this mapping to the complex number to 1, and this vector to the imaginary unit I. You know that the vectors 1, 0, 0, 1 form the canonical basis in R2, and correspondingly the vectors, the complex numbers 1i, these two complex numbers form a basis in this vector space in C. This is exactly the representation of the complex numbers in this basis. I shall write once again here is x. We can consider x times 1, the first vector, plus y, I, where x and y are real numbers. So this is just the description in this. We can consider it the canonical basis here. By using this isomorphism allow us to identify the two vector spaces, and we use for the space of all the complex numbers the same representation, a geometric representation as for this real space, two-dimensional real space. So we consider here the system of axes, and if here is x, y, at this point corresponds at the same time to the vector of components x, y, which we identify by using the presented isomorphism to the complex number x plus y. For example, here this canonical basis here is the complex number 1. At the same time, this has the coordinate 1, 0, and the second vector canonical basis here is I identified with this 0, 1. Now on the space R2, the formula norm of x, y equals square root x squared plus y squared. This defines a norm. Norm on R2, but you can remark that exactly this x squared plus y squared is exactly modulus of x plus y. So C, the space, the vector space, real vector space of all the complex numbers considered with this, with the modulus, is a normed vector space. And here, evidently, on R2, you know that considered together with this norm is also a normed vector space. The considered mapping, we already remarked that C can be identified to the space R2. We identify the complex number x plus y. We identify with the vector x, y, but the formula we have already presented, norm of x, y, which is square root x squared plus y squared equals norm of x plus y I. We can see that these vectors have the same norm, so C can be identified to R2 are identical as normed vector spaces. They differ, just the notation is different, but the addition, multiplication with the real scalar, the norm, are defined very, very similar. Now, by using the norm, we can define the distance. I shall remind you the distance between 2 points in R2. Let us consider here again, and we consider 2 points here. Let us here be x1, y1, this point, and another point here is x2, y2. Then the distance between the 2 points can be easily computed by using this right triangle, and evidently this side of this right triangle is x1 minus x2 squared plus y1 minus y2 squared. The length of this side is evidently this difference modulo. So the mapping, the distance between the 2 points x1, y1, x2, y2 is equal to square root of x1 minus x2 squared plus y1 minus y2 squared. But this is exactly modulus of z1 minus z2, where z1 is the complex number corresponding to this vector x1 plus y, and z2 is x2 plus y2i. So the distance between this point, here we represent this vector, and at the same time the complex number z2 is here, and here is z1. So in the complex plane, the distance between 2 points is just the difference. Z1 minus Z2 modulus is distance between Z1 and Z2. Evidently, modulus of Z, which can be written as Z modulus of Z minus 0, is the distance from Z to 0. Now, by using, you can remark that C can be identified to R2 by using the indicated isomorphism also as metric spaces. The presented isomorphism keeps unchanged the distance between two vectors. By using the distance, we can define, for example, the disk. Let us consider here Z0, radius R. We denote this disk in the following way. And this is formed by all the points Z, such that the distance between Z, the distance between 2 points is Z minus Z0 is less than R. This is the disk of center Z0 and the radius R. The two spaces are identical as metric spaces, so they have the same topology in the space of complex numbers. A set is an open set. Let us consider a set here, D. A set D is an open set if for any point Z0 is that there exists a radius, that epsilon, such that the ball of radius epsilon and center Z0 is contained in D. This for any Z0 from D, there exists such an epsilon, positive epsilon. Now, as concern the convergence of sequences of complex numbers, we have the following relation, very useful. let us a theorem for any z equals x plus y I from C. We have modulus of x plus y I is less than or equal modulus of x plus modulus of y, and at the same time greater uh, uh, greater than modulus of x as well as modulus of y. We can easily prove this relation. For example, one of these inequalities, modulus of x plus. By definition, this is square root plus y, and this is evidently greater than or equal square root of x squared, which is exactly modulus of x in a similar way. And for this, it is sufficient to consider the square of this lesser than the square of this, and to compute. And we have the following result. Limit of a sequence xn plus yn I is alpha plus beta I for n going to infinity. We have this relation if and only if limit of xn is alpha for n going to infinity, limit for n going to infinity yn is beta. You have just to use the definition. This is equivalent to limit of the distance between this and the distance between this number and this one is just modulus of the difference xn plus yn I minus alpha plus beta I, and by using this theorem, this is greater than or equal to modulus of xn minus alpha as well as modulus of yn minus beta, and at the same time the sum xn minus alpha plus yn minus beta. And from this double inequality, you can easily obtain this result. So we have C is identical to R2 as normed vector spaces, also as metric spaces, but C has an additional structure given by the multiplication of complex numbers, which does not have any analog in the case of this real vector space. Multiplication of complex numbers is an additional structure existing here but not existing here. But we shall discuss this in more details in a next video clip. Thank you.